Hello, and welcome to Group 14's Thermofluids video report. Here we have a laminar flow cabinet, or often referred to as a safety hood. These are used in industry by chemists and by laboratory workers very often, and this is because of one important reason. Often, whilst working in industry, chemists or laboratory workers will have to be dealing with potentially hazardous, toxic, or carcinogenic materials. When they perform these experiments, it's really important to keep the contamination of the lab, like the risk of contamination, at minimum. And it's really important to keep the experiment isolated so that it's not affected by external factors. It's in these instances that our group will look to investigate what it is that can disturb this laminar flow and what it is that can transition the laminar flow into a turbulent flow. As such, our research question is as follows. What is it that determines the transition period of the flow of a liquid inside a sealed container, such as the laminar flow hood? To demonstrate this, we'll be using the following experiment. We will now consider what it is that determines whether or not flow is either laminar or turbulent. First of all, we know that the laminar flow is a result of inertial forces within the tube given by the liquid. We also know that turbulent flow is given by the viscous forces within the liquid. It was Reynolds who first came up with this idea and realised that he could create an arbitrary unit, dimensionless, which would also, for any given liquid, that would describe whether or not the flow at a given flow rate was turbulent or laminar. First of all, let's consider any liquid passing over a surface. If we consider the liquid to have an initial velocity of u, and this velocity to be at point y above the surface, we can think about the shear stress that is on the liquid as friction is caused as it passes over the surface. As we become closer and closer to the surface, friction slows down that layer of the liquid, causing the velocity gradient. This can be expressed by du over dy. Now, we can say that the shear stress is equal to a coefficient of viscosity for a given liquid multiplied by that viscosity gradient, which is du over dy. So if we go back to the ratio of inertial forces to viscous forces, we first of all need to describe what an inertial force is. This is the mass times the change in velocity. Or if we say it's the mass divided by time, we can assume this to be the mass flow rate, multiplied by the cross-sectional area, for this case d squared, multiplied by the velocity, u. This gives the forces to be rho times d squared times u squared. Now if we consider the viscous forces, we have the shear stress times the area. This gives the coefficient of viscosity times u by d times d squared. So now if we divide one by the other to create our Reynolds number, we have rho times d squared times u squared divided by the coefficient of viscosity times u times d. If we simplify this down, we have rho times d times u divided by the coefficient of viscosity. Then if we take this term and call it the kinematic velocity, we can simplify the equation to be u times d divided by the kinematic viscosity. This gives us the mathematical equation for the Reynolds number, which allows us to figure out for any given liquid whether or not at a given flow rate, whether the flow will be laminar or turbulent.
In conclusion, there was numerous of ways in determining the type of flow we were able to see. One of them was by increasing the temperature of the water from 23.1 degrees to 42.4 degrees. We were able to see a more uniform turbulent flow. When we put the sponge mesh in, there was a laminar flow. When we put nothing inside, it was both laminar and turbulent flow.